All right, well, good evening. Welcome, everyone. We'll get started here. I'd like to welcome those watching on the live stream, and welcome those who've come here in person on an overcast night, but there's still opportunities to learn, right? My name is Drew Desker. I'm the director here. Great to see some familiar faces. But looks like a couple of new faces for me. Who's here for the first time or haven't been here in a while? In a while? Okay, very good. Well, we do this every Friday night, regardless of sky conditions, and it's really an opportunity for us to sort of remind ourselves how much fun and interesting science and engineering and technology can really be. And there's no test at the end, right? At least not this time.
Not this time.
Okay. So again, I also welcome those that are watching on the live stream. So today's going to be quite an interactive day, so there may be a little bit of camera movement here. But I'm really very happy to have Peter Klimas back with us. Peter, you have the very unique distinction of being the last live performance we had here before we had to shut down in 2020. And so although we're not quite out of the woods, we are in fact at least on the edge of the woods, and so it's great to be able to do this again. And actually, what's been nice is it's actually given us an opportunity to get our live stream audience connected. And so again, what Kopernik's really all about is helping people understand how the world works. And we're not necessarily trying to turn everybody into a scientist, although it actually is a pretty cool thing to do, is to be a scientist, just saying. But ultimately, we're really trying to promote lifelong learning. And again, Peter's been a great resource to us in the past, and this is the first time he's done this particular presentation, so I'm really looking forward to it. So we're going to just turn it right back over to you, Peter, and take it from there. Thanks.
Very good. Thank you, Mr. Desker. So, for the folks at home, right, we're going to challenge Mr. Drew Desker here to see what he can do with all these demos. And for all of you here, welcome. I'm glad you're here tonight. This is not only the first time I'm doing this for you guys, but this is the first time that I've put all this together as a presentation. I've done a lot of these in my classes. I'm a high school physics teacher at Vestal High School. And so all these demos are familiar to me, but the actual, the togetherness of it, we'll see how it goes, right? We'll see how all this goes tonight. Right, to echo, right, I was going to say, I hope you find this informative and entertaining, right? Entertaining, maybe even more so than informative, but we'll see. So tonight's demonstrations are about waves. And it was kind of hilarious to me because I have a colleague at work who was like, wave demonstrations, so you're going to like demonstrate, right, how to wave. You could like do different waves. You could do, and I was like, nope. And then on the way out of the building today, I had another colleague at Vestal High School because this was kind of the picture that was up on the site, and this was kind of like advertised it. And this other colleague was like, "Oh, good luck on that water thing that you're doing." And I was like, "Yeah, okay, thank you." So right, for that bigger context, right, there are a lot of physics class that we do in the beginning of the year that is all about, right, particles, right, or as I would like to say more familiarly, like baseballs, right? That's what we're talking about. We're talking about objects, about things, and how things, right, can move and go at different speeds and accelerate and fly through the air and collide with each other. And it's like things, baseballs, right, or particles. But then finally you get to this point where you realize that you have to go to like the new genre, right? When there used to be CD stores and you can get your music there, right? You've got like the different sections where there are different kinds of music, and you need to like listen to a different kind of music, right? Because the game that you've been playing can only go so far. The phenomenon, right, of reality, of the universe are more than just baseballs, right? There are things that are different. And one of those things are, right, what we would describe as waves, right? So could we like call them out like a kind of wave? Like one of them would be, ooh, say it. Yeah, sound waves and water waves and
light waves
and
sound waves
sound waves and Do we have any others, right? Like, ooh, like radio waves, yeah? Now, this is where I like to say you're prejudiced against light, right? Because light, right? Light is really, in physics, this electromagnetic spectrum. And so there's actually all these parts of the light spectrum. We like to think of light as just the light that we can see, the visible part. But of course there are, ooh, do you know any of these other parts too?
Infrared.
Yeah, infrared and
Ultraviolet.
and what did we say already? Was it X-rays, yeah? And gamma rays and like microwaves and radio waves. And so we have all of these kinds of waves, right? And then in addition, I'm going to like show you some other ones tonight. All right. So I was on vacation, and I took my vacation photos here. You okay? Okay, good. Ooh, yeah, there we go. And so we were throwing rocks in the pool, and right, and so then I got this like nice series, right, of how this wave moves through the water, right? The wave propagates. And this kind of question that I like to think about, even after all these years of teaching physics, right, is the water the wave? Or is like the wave this other thing that moves through the water, right? That's kind of what makes waves interesting, right? That the waves seem to be like they are the water, but at the same time the waves aren't the water, right? So another kind of wave, right, that we didn't mention was we could do some slinky waves. You want to be my volunteer back there? Victor, thank you. All right, and so we're going to take a look at some of these slinky waves tonight. You guys, look out of the middle aisle here.
Mark, you're going to move your feet there.
Good, get like a good, right? And so I like to start, because you can see this very visually. Feel free, right? Stand up, move around, get where you can see here. We're going to just throw some waves here back and forth on the slinky, and we can watch these waves move. And in the same way, right, that we say, is the water the wave? It's the same question here. Is the slinky the wave, or is like the wave something that moves through the slinky, you know? Because certainly like this coil right here, you know, it's going to be the wave, but then it's not, right? The wave's down there and it's coming back and forth. And so the waves move through matter, but like they're this other thing, yeah? Like, yeah, right? Like, I don't have a good answer for you, right? There's no, right? It's the mystery that lasts, right? Not the explanation. And so in the same way, sound are waves, right? Sound is coming to your ear. I like to say that you can hear me right now, but you don't have to smell my breath, right? My breath is here, right? Those are the particles, but my sound waves are coming very clearly to your ear all the way in the back of the room. And so these waves, right, they're propagating down and back and forth on the slinky. And in physics, right, there are some different kinds of waves. One kind of wave is the waves that I've been making, where I'm going to move my hand sideways, but the wave is going to go back and forth down the slinky. And we call these transverse waves. Let's get some audience participation. Say transverse. Transverse. Yeah, all right. But then there's like another kind of wave that I can send down the slinky, and I could do that or I can pluck it. And this is where I'm moving the slinky coils along the direction of the wave. These waves are called longitudinal. Say longitudinal. Longitudinal. Now, longitudinal's got another name. It's called compression. Say compression. Compression. Ooh, compression. Now, I've also heard these guys. Wait. What kind of waves were these? Transverse. Ooh, transverse. I've also heard these guys, transverse, be called shear waves, right? Because there's like a sideways motion to the wave, right? And then the wave goes perpendicular to the way that you move. Or, right, there's along the wave. So two different kinds. It turns out, right, that sound is our compression wave. My vocal cords, I'm compressing the air, and that compression is beating on your eardrum. But a lot of other waves, like, you know, these slinky waves right here, and water, these are transverse waves. Light is a transverse wave. And a lot of the other examples of waves are transverse. There was one kind of wave that nobody mentioned that can actually be both. Well, slinkies can be both, but there's another kind of wave that nobody said earlier. Starts with the fancy word starts with an S.
Sine wave.
So sine waves is a mathematical description, but seismic waves, yeah? There are P waves, the primary earthquake comes through as a compression wave, as a longitudinal, but then the secondary, the S seismic wave, comes through as a transverse. All right. Now waves, they've got little guys and they got big guys, and we can describe that with a thing called amplitude. Waves can be like this or like this. Can you think of a word to describe the difference between these waves that I've made? These guys versus these guys right here.
Frequency.
Yeah, the frequency. So we've got like the high frequencies, right? And then we got the low frequencies. There's the other words that could go with the same thing. Like the high frequency waves are also... Ooh, they're short. They got a short wavelength. And the low frequency waves have a longer wavelength, right, like that. And then we could even talk about the amount of time it takes me to make the wave, the period of the wave, and finally, the speed of the wave. And the speed of the wave is actually the most interesting thing. I can throw a little guy, and it gets to the other side, comes back to me. I can throw a bigger guy, and it gets down there, and it comes back to me. Little guy goes down there and back to me. Like high frequency, maybe like a lower frequency. Now that lower frequency, it takes me time to make it, so it kind of gets all elongated, but the very front end gets down there to the other side. And the little guy gets down there to the other side. And the big guy gets down there to the other side. The speed of the waves, I don't know if you're noticing this, are pretty much the same, yeah? Should we make it faster? Yeah, should we make it faster? So waves, right, the speed of a wave, it turns out, it doesn't matter how loud or soft I talk or high or low I talk. It's the air that determines the speed of my sound waves. And it's the slinky that determines the speed of the slinky waves. What we just did, we gathered up some of the slinky and we made it more tense. Check this guy out. Yeah? The wave speed just got? Faster. Definitely faster, right? So in physics we say that the speed of a wave depends on the medium, the stuff that the wave moves through. Let's come together a little bit. And I just let out my coil that was in my hand. And we're really making it a lot looser. And now we can throw some of these guys a little bit slower, right? As that slinky itself has changed. In the case of sound waves, it's the temperature of the air that determines a lot about the speed of sound in air. In the case of water, it's the depth of the water.
What about light waves?
And what about light waves? It's literally the stuff that they go through.
What are they going through?
So in the nothingness, right, which is a very, very, very crazy idea, right? Through the nothingness, light travels at its fastest, right? 300 million meters a second. But when light goes through water, it travels a lot slower. When it goes through glass, it travels a lot slower, right? Anything transparent is going to slow down that speed of light.
But it seems like up into that, it's like higher density is faster.
Yeah, so this is where it's like we have in the studies of light, we have this term called the index of refraction, which some people refer to as the optical density, which isn't necessarily the same thing as the density, right? But here we've just got the optical density, and it does turn out that the stuff that the waves go through determines the speed of the wave. All right, so we've got those slinky guys, and I'm just going to go to the next. No problem.
All right.
Yeah, I'll just advance to the next one. Here we go. So then I built this other wave machine, right? So we have these other examples of more like science-oriented waves, like sound and light. But then you're like, yeah, but I like the slinky waves. And I saw this guy, and whenever you see something like this, you're like, dude, I got to make that too, right? And so we've got here, right, a gummy bear and shish kebab waves, But here again, it's the saying in physics is that the speed of a wave depends on the medium, right? The medium, the stuff that the wave moves through. There was that show on TV a while back, Long Island Medium. The woman who communicated with the dead. She is the medium through which the dead communicate, right? In the same sense that the medium is the stuff that the waves move through. So in this case, right, you could actually think about I can think about a bunch of different ways to change the medium, to change the speed of the waves down this thing. One thing is the tension, just like the slinky. We could really tense this up. We could make it a little bit more slack. But another thing is we could take off the gummies. We could eat all the gummies, yeah? And then there would be less mass, right? There'd be less inertia for this to be, right? It would be less massive, and so it wouldn't propagate as quick. It would propagate quicker because it would be easier. We could add gummies, right? We could put 2 gummies on each end, and then it would be slower. And so we could vary that medium in a variety of ways. With the gummies, we could space out the sticks. We could shrink up the sticks. We could play with the tension. And so all these little tweaks would then alter the speed that the wave propagates through. The speed of a wave depends on the medium. It depends on the stuff that it goes through. You ready? Let's just send a couple here. Ooh, after I had this set up in my classroom, I realized I could do this, right? You don't have to do it at the end. You could be like, wah-bah, ooh, and then we get to going, come bouncing, and coming back. All right. So then what's next, right? What did I do next? It's a good thing that I made this presentation. You're like, what's going to be the next slide? It's so exciting. Ready? I'm ready. Yeah. Oh, yeah. So, right, so we showed you transverse waves, and I just wanted to do another example of it right here. A stadium wave, right? Like, are the people the wave? You're like, well, of course they are. Well, you know, like that thing moves through the people, and you certainly need the people in the stadium to have the wave, right? But like the wave is this other feature that moves through the matter, or does it move through the nothingness too, right? Like light. And here it comes around, right? This guy's watching the game, but did it go there? Oh, there it comes. There's, here it comes, right? The people are moving up and down, but the wave is moving side to side. There's your transverse wave. And then the best kind of picture that I have here is of a longitudinal wave. The great longitudinal wave is sound, where the air gets compressed, right? And you feel that compression, right, in the form of sound with this very sensitive eardrum that we have, right? That eardrum gets beat on, and you perceive that sound. I don't know about you, but I've been to concerts where the sound is so loud that you can feel the compression of the air, right, on your body. Yeah, bah, bah, right? It's so loud, right? You've got to get your earplugs in. But here we've got, right, the same idea of the wave where there's this compression of the air molecules and then this, right, spread outness, this compression, and then this distance between each would be this idea of the frequency, right? How often that's beating on the eardrum or how infrequently. All right, so there's kind of some of the basics here about waves. And for the rest of the time, I wanted to kind of fit together some more demos of kind of three interrelated ideas. The first of these is interference. The second of these is going to be about standing waves, and the third is about resonance. All right, so I'm going to come back to these three. Interference, standing waves, and then resonance. So waves, right, are fascinating in that they can do things that particles can't do, right? And one of those things is that they can interfere with each other. When two or more waves exist in the same medium at the same position at the same time, they're going to take a superposition and interfere with each other. Now, we're all in the same room tonight, right? Like we're at the same spot, but we're not in the same place exactly, right? I'm not literally sitting in the space, in the chair where you are. We can get close and like touch, right? But like we're still not in the exact same space. But waves can be in the exact same space, right? We can speak and we can all speak over each other and all those sounds come to your ear at once. Now, I think our consciousness will zoom in and focus on one of the sounds that we want to listen to, but all of them are beaten on the eardrum, right? They're all there simultaneously at the same spot at the same time. And one of the ideas that I like to think about when I think of this is the Hufflepuff ghost from Harry Potter, right? And in Harry Potter, they'd be walking through the dining hall and the ghost would like, like give them everybody the shivers when the ghost would like move through their body, right? It was literally occupying the same space at the same time. And so with that, all right, we've got here two kinds of interference. And let's get this a little more animated version right here. So what we're going to do here is this a little simulation from the website fet.colorado.edu. They've got a lot of good educational simulations. And we're going to send a pulse here down this string, very similar to the slinky, right? Only here, we've got, I turned off any damping, right? So that slinky wave died out because the carpet and the slinky, there was some friction, and it killed the wave after a couple times back and forth. But here, we're going to let this guy just go back and forth and back and forth and back and forth. Now, an interesting thing about waves is that if instead of holding the end firm, right, and if you noticed how it was flipping there, it flips back and forth and it flips back and forth, if you kind of let yourself be loose, you can let that wave come back on the same side, right? You can kind of just let it move your hand, and then it keeps that wave where it was. So now we're going to send another wave at it, whoop-ah, and the two waves, bam, at the same spot at the same time will occupy that same position and interfere. And then we have a name for this kind of interference where the waves make themselves bigger than either is individually, and we call that constructive interference. You want to say it?
Constructive interference.
Yeah, all right. So that's one kind of interference, right? They get bigger because they're at the same spot at the same time. Now, the other, it's not what I wanted to do, the other kind of interference would be when the waves take away from each other. So this time, we're going to let this guy flip on the other end and send another wave at it. Whoa! And then we're going to watch these two come together, whoop, right there. Now, it happens quick, right? But the one is up and the other is down, and oh, let's pause it. And let's inch it through, inch it through, inch it through, as these two waves are right on top of each other. And it's almost like, right, they've completely, it's like there's nothing there. But there is something there, right? That energy is still there, right? And if we press play, we can, oh, there they reemerge, right? The waves pass through each other like those ghosts in Harry Potter. And when they're at the same spot at the same time, they can add to be something bigger, or they can take away and be something smaller. So then, right, where are we? Right, we're good?
Nope, actually,
But we're not.
Yeah, we're going to that one.
Yeah, that one. All right, here we go. Ready? Yeah, I got it. There you go. Yeah, it's the same. That's all right. We could re-up it, I think. Nice. See, we're in the same spot. Destructive. This is called, ready? This is the old school, right? Is all the technology going to work? Well, if you make still pictures, you can go through them, and it's like a movie anyway. All right, but the slinky, right? The slinky can be made to do some of the same stuff, right? So check this out. Ready? We're going to miss. Oh, we missed the two end ones, but we knock over the middle because those two waves were small enough to make it through the channel, right? But when they're at the same spot at the same time, bop, they bop that middle guy down because they add together. That's constructive interference. But we could also do kind of like a destructive interference with a slinky where, oh, we can knock those guys out, but then as they merge together, they take away from each other, and they don't knock over, right, that middle one because they're at that same spot at the same time. All right, so let's see if we could do another little switcheroo here and show everybody. Oh, I was there, I'm sorry. Yeah, I'm slow. All right. So let's listen to some music tonight. Right, we've got is a program. It's a free program. It's called Audacity. Right, so you could download this and just do a little music editing with it. But I have a track in here from Skrillex and the Doors compilation that I enjoy, and let's just listen to it right here. I've got everything muted except for this first track. You can see that blue track right there, and we'll press play. Now, let's zoom in a little bit on the signal here that we're listening to. Yeah, you hear that bass beat come in, and as that bass came in, you see these long waves, right, that are kind of like oscillating all the way across, right? That's that low frequency waves. But all on top of each other are all these sounds, right? There's all these sounds together. They're, in a way, interfering with each other, but in a very positive way, right? Like a pleasurable way that is music. But you see that low frequency stuff, and then you see that higher frequency stuff that's on top. Ooh, it's getting quieter, small amplitude, right? And so it dies down and it's quiet. But then that sound's going to pick back up again, and the amplitude of the wave gets a little bit bigger. But all those frequencies are layered on top. The really high stuff is on top of that lower wave that kind of arcs across the screen. Alright, so now I've got another track here that's the exact same thing. Let's see if we can hear it. Yeah, it's subtle. Can you hear it a little bit? Yeah. And when we put the two signals right on top of each other, playing the identical thing, a little bit louder. I've even got a third one that's identical. A little bit, yeah, a little bit. All right. Now, on the bottom, I've got a signal that I inverted. Let's listen to that. Let's mute this guy. We got them all muted. Here's the inverted signal. And if you can catch it, right? When this guy is like down, it's flashing through the clip, right? But it's upside down. but the sound is the same, right? It's the frequencies that we're perceiving. And so when the speaker is out, now it's in, and when it was in, now it's out. But the oscillation of the speaker is the same, right? It's the same frequencies until we hear that same music keep playing. But if we play now the inverted signal with the original, we can cancel the signal, right? And now, essentially, right, the speaker is being told, be nowhere, right? Be up and down at the same time. And we can then, right, just play the inverted. But when we play the both, destructive interference and the signal's canceled. All right. Now, right here, I like this, right? I even got a good reaction tonight a little bit. Ooh, where I got little faces going. That's good. I like it. But I am a little bit disappointed, I have to say, because the sound isn't being really canceled in this room. The sound is being canceled internal to the computer, right? The computer is being told, be here and be here, and so it's nowhere, right? Even though it's being told to play stuff, the ultimate end product of the math is just don't do anything. And so the speaker doesn't move. And so we don't hear anything, not because the sound is truly being canceled in our room, but rather because, you know, it's internal. So I said to myself, is there something that I can do that would be more of a, you know, like real effect in the room? And the answer is yes, all right? So what I'm gonna do here is I'm gonna generate for you a tone tonight, and this tone is gonna be 255 hertz signal. It's a sine wave. It's gonna be kind of annoying, all right? But we're gonna play it for you right now. It looks like a big blue bar, but if I zoom on this thing, zoom, 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 all right, what you see is that it's just the speaker's going to oscillate in and out, and it's going to oscillate in and out at 255 hertz, or 255 times per second. And so I had to zoom way in, right? Because now you're seeing a whole bunch of oscillations there. I mean, this is, you know, you're talking about, what there, 1/100th of a second, and you're getting a couple oscillations in. Right there it is. But what does 255 sound like? Well, it sounds like this. I've got this tuning fork over here. Yeah, that's a note, yeah? Quiet. Right, that's the note, you heard it? And then this is the note right here, you heard it. You ready to play them together? Don't get dizzy. And then you're like, wait, stop. It's just that note, right? It's just that note. So I've shown other physics teachers this. You got to get this one on camera, right? Am I on the camera frame here? Right, I've shown other physics teachers this, and they're like, oh, I can't do this, Pete. Right? And I'm like, no, you got to show everybody this, right? So they're a little bit off, right? They're a little tiny bit off. Now, this is a phenomenon that we call beats in physics, which is not the beat of that music that we were listening to, right? That's a legitimate use of the word beat. But a physics beat is where you've got these waves that are ridiculously similar, right? So essentially they're together. But over the course of a lot of cycles, right, the one starts to take the lead, right? So it takes the lead here. And instead of being in sync, they start to get out of sync, right? And now they destructively interfere with each other. Then over the course of many, many cycles, right, you get this one catching up, oh, and you're going to get the constructive interference again, and it's going to go, and it's going to get out of sync, and they're going to get destructively interfering, and then over many cycles, it's going to catch back up, and you're going to get this constructive interference again. Constructive interference was when the signal was louder, and destructive interference was when the signal was softer, and we could hear that. Like, it was a little louder, and then it was a little softer, and then it was a little louder, and then it was a little softer, right? That louder, softer that we heard is what we would call a beat. So they're a little bit off. Now, I can tell you that that tuning fork says that it's 256 hertz. Yeah, I generated 255. And so let's mute this one. I'll keep this guy around. Let me just zoom back out so I know that I'm doing the right thing here. Zoom back out. Let me click down here. Let's generate another tone, which is 256 hertz. Okay. And you can listen to this one. Is it 256?
Nope.
Yeah, no, right? It's not. Yeah? Now, do you hear how that slowed down, though, right? Do you hear that little, that slowing down? It means we're getting closer. So let's mute that guy, and let's generate a tone that is 257. We were moving in the right direction, right? It was getting closer. 257. Okie doke, I did it wrong. Undo it. I don't know if that undid anything, but we'll see. Generate a tone. That is 257. That's what I wanted right there. Yeah, 257. Mute, play. Pretty good. Yeah, pretty good. And I also think that these two are also a tiny bit different from, they might be like a half a hertz different or something like that. Ridiculous, right? There it is. I like it. Now, let's go the other way, because that got a little bit hard to hear, right? That got a little bit harder to hear. And so what's not hard to hear is to generate a tone that's even more off, right? I started with 255. Let's go to 253. Yeah? Let's go to 253 and generate that one. Again, I did it wrong. Control, undo, click off of there. Generate a tone that is 253. That looks good, right? Like that. Mute, mute, mute. Got the 253. More frequently, they're getting into and out of sync, constructive and destructive interference, constructive and destructive. And in fact, right, that if it's really 257 and this is really 253, there's a difference there of 4, right? 4 cycles every single second. And so we should hear 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 every single second. We should hear 1, 1, 1, 1, 1, 1, 1, 1, 1, right? 1, 2, 3, 4, 1, 2, 3, 4 every single second. That would be what's called the beat frequency of these interfering waves at the same spot at the same time on your eardrum, right? Not just internal to the computer, but actually right here in this room. All right, let's keep it going. PowerPoint, that's the one. Look at that. That was the music that we heard. That was with a tuning fork really here in this room. And we're going to move on here to another little phenomenon, the second part of this, which was standing waves. All right. Let's come back to that. Let's do it. Here we go. Some standing waves. You ready? Ready? All right. So a little bit of danger, right? For the front row here, you guys got to watch out. I don't know. I'm going to come over here. Be careful.
Hold on. I got to.
All right. Yep. Yeah. Get it set up. All right, so some waves, right? Some waves, if you put them confined to a space, they will persist. They'll persist in a regular pattern, and we call that a standing wave. So I can, right? You ready? I can just create some random jiggling here, and this random jiggling here is just going to kind of die down, and it doesn't really create anything of persistence, right? But what we can do is we can start to generate a wave, right, that has this pattern that persists. And we call these the harmonics. And this one would be the first harmonic. This would be the fundamental frequency, or the first harmonic. And this pattern right here, you can think of it as I'm throwing a wave to Mr. Drew Desker, and it's bouncing off and it's coming back to me. Throwing it back to me. Throwing it back to me. But Drew's also throwing one to me, back to him. To me, he's throwing one back to me. We're both throwing waves at each other, and these waves are interfering. Now they're hitting the ground and they're really getting some jiggling, right? But these waves are interfering with each other, and they're creating this pattern that persists. Now that's kind of a boring pattern. We can get a more fancy pattern. Are you ready?
Good.
All right, so then we get the second, right, most fancy pattern that persists, and this is called the second harmonic, right? The second most complicated wave that stands. And in the middle of this standing wave, you've got a spot that kind of doesn't move. If we were doing it perfect right there, you could say that spot doesn't move. That's called a node. And you got two spots, one on my side, right, one on Mr. Desker's side, that is a anti-node, a spot that bounces the most, right? So that's the second. You ready for the third? Right? Oh, now that's like not the right. Now I got to get the right frequency. A little faster, maybe. A little faster. Come on, come on. No, that's not it. Let it die down. Let it die down. The frequency's got to be just right, right? Or you don't get that standing wave pattern. There we go. Yeah, like that. Like that. Yeah, right? There's the third harmonic, right? A pattern that persists. Right? There it is. But the frequency's got to be right. If I don't get that frequency right, you don't get the harmonic. That's good. Thank you. And you can keep going, right? It'll get harder and harder to do. I was having a hard time with the third one. I was like, let's not go for the fourth, right? But the patterns here, right? You could go, right, from that simplest one to the second to the third to the fourth, right? And you could keep going on, the fifth, the sixth, the seventh, the eighth, the ninth. And this would be a very visual representation of those standing waves right on the slinky. You're doing a great job. All right. But a lot of musical instruments, right, they also generate standing waves, yeah? These things generate standing waves here, right? If you whirl them around. Yeah, you want to try that? Try that out. You go ahead, stand up. Don't hit anybody.
Away from your parents, exactly.
Right? Don't hit. Just whirl it around. Whirl it around. Oh, do you hear these different notes? Right? These different notes are the different harmonics that are being like. I heard that one too, like this one right here. And there's even one more. Did you hear that? I can get the let that kid have it. Let's get the here, I'm gonna get it. I'm gonna get it super slow. Ready? I gotta get like Alright, and then the last one goes like this. Oh, I can barely hit the one. Alright, back it up, back it up. Let me go. Alright, sit back down. You had the fun little ready? And then there's like right? Really up the next harmonic up. I also discovered that you don't have to whip these things around, because when you whip them around, what you're doing is you're winging air out of them. And if you have like a sweaty hand, or if you dip your hand in some water, right, or in the olden days, if you could just lick your hand, right, you could then put it right here, and you could feel the air, right, being drawn into the tube as the other air is flung out the end. But so you could whip it around, right, and produce that note, but you could also just pass air through it. Right, and you're hearing some of those notes depending on how quickly the air is being moved through. Now, these have got ripples on it, right? They've got ripples. And the ripples make the air tumble a little bit as it goes through there. And that tumbling air then jiggles and vibrates and creates those different harmonic sounds. But you can also, right, produce some notes with some harmonics here, with just like a regular piece of PVC pipe. Right, there's that note. And that note depends on how long this is. I can cover it. Again, annoying for your ears. You ready to hit some of the higher harmonics here? Right? Oh, getting some of those higher harmonics, right? Getting some of those different vibrational patterns. Now, if the end is open, you can get the pressure of sound to jiggle in what's called that antinode, right? The antinode was those spots that were jiggling the most. If the end is closed, then you get what's called a node, a spot where the pressure can't vary really because it's closed off to the end. And so you can hear this open end note. Meh, meh, right, that note. Meh, meh. Right, you're getting two different notes, and if you're familiar with music, these two are octaves, right? These two are octaves here that you're hearing. And so then what you could do, right, is you can get, oh yeah, right? You can get some other tubes here, right? And right, these guys, you just, let's play those notes, right?
Oh, I gotta see. Is there another C?
Yeah, there's another C right here. But it's not the same. Instead of listening to these fools, right, we could check out.
Hold on, get it back to this.
Can I have one?
But you're agitating, right? You're agitating the air that's inside the tube, and you're making it to vibrate in a standing wave pattern. A pattern that has an antinode on the one end and an antinode on the other end if the ends are open. But if you close the ends, you can make it a node and have the sound vibrate that way. And you get a different note with different length tubes. Because the longer the tube, the lower the frequency, right? And the shorter the tube, the higher the frequency that's generated, because that note has to be, right, kept in that shorter tube, generating a higher note. This guy's really
Green one. No.
Yeah. All right, so, right, lower, higher. But you put an end cap on it. Same, right? Here, antinode, antinode. Here, antinode, node. It brings it down an octave. And taking that off brings it up an octave. All right. Then I came across this guy playing on the street. All right, there's some great videos. The curator of all the YouTube videos here for you tonight. All right, but this guy, he's got this great machine that instead of hitting them, right, he's hitting them here, right on the end, with his flip-flops. Now, what's great about this one is that you realize the tubes don't have to be straight, right? You could bend them all up and make this nice little setup. You don't just have to hear them, right? I showed you a slinky. But down in PA, I think some physics professors built this bridge. And this bridge was made to oscillate, right, in these different standing wave patterns. So here is, we showed it to you here tonight with a slinky, but here is a second harmonic on the bridge, right? And these guys are standing at a antinode, a spot that moves the most, right? They're peak, trough, peak, trough, peak, trough. Now this guy's going to come into the other antinode, get on that antinode, right, and oscillate. But in the middle, there's kind of a spot that doesn't move, right? In the middle of the bridge, you would just be messing things up trying to get into that spot and bounce on the bridge.
Okay, what I want to know is, how many adults would do this?
Yeah, right?
A couple. How many kids would do this? All of them. All right.
All right, so let's just check out a little bit more. The third harmonic, so, right, you got to coordinate. Now the third harmonic, that was harder, right? The third harmonic's got 3 of those lobes, right, that are oscillating. So instead of just the 2, you got to have 3. And the bridge can only bend so far, right? So it can bend, but it can't bend too far. And so here you got a little bit of a smaller amplitude because you got to get it into this third mode of oscillation.
I'm thinking all swim.
But a pattern that persists. Now, a really famous example in engineering is that out in Washington State, turn it down, there's a louder one. Out in Washington State, there was this bridge, the Tacoma Narrows, right? And the Tacoma Narrows got into exactly these sorts of oscillations, but not intentionally, right? This was gusts of wind coming through and getting this bridge into these standing wave patterns. But what's crazy here is that, right, you've got concrete and asphalt and steel, right, that are being made to vibrate, and they can only vibrate so much before, right, that bridge is gonna, right, rip apart and go down into, right, the Narrows. Let's go find it right in here, Ooh, that car on the bridge. Now, you can also see that there's these torsional modes of vibration, right? Rather than the up and down, you can twist. You can have these twisting vibrations, and eventually, right, the bridge is going to rip because it can't go into that. All right, last part of the presentation. All related are, right, the waves are in the same spot at the same time, so therefore they interfere. If they get bigger, constructive. If they reduce, destructive. If that sort of interference is a way of a pattern that persists, then we get this thing called standing waves. And finally here, right, we get into this idea of resonance, where the waves will interact with objects, right? And so when the we're going to force stuff to vibrate, but if that vibration matches the natural frequency, then we're going to get this big increase in amplitude. All right, so a little demonstration here though first, this concept called natural frequency. Right, so I've got these two things. I got a protractor today and I got a pencil, right? And I'm going to drop them on the table here, right? And we're all going to close our eyes. Ready? Close your eyes. I'm going to drop one of them. Don't look. Don't look. You tell me which one I'm going to drop. You ready? Don't look. Let's listen.
Protractor. Protractor.
Yeah, that was the protractor. Yeah, do you want to hear the pencil? You could open your eyes because now you know it's the pencil. Yeah, that's different, right? There's like a sound that the one makes, right? And there's like a sound that the other one makes. There's like a natural frequency that's associated with that object. So if we can get into that natural frequency, then we can cause things to really start to jiggle, right? We can really get things going with this wave interaction with matter. But we've got to do it just at the right frequency or nothing's going to happen. Good job switching. So a swing is a great example. Now there's going to be some text that come up that I don't really care about, but a swing is a great example of resonance. So if you just swing your legs wildly, right, you don't get into the natural rhythm. And you want to get into that natural rhythm, right? You've got to swing those legs forward when you move forward, and you've got to kick those legs back when you move back. And if you can get into the rhythm here, oh no, that wasn't, because swing your legs forward, come on son. Swing them forward, right? Oh, there you go. Yeah, oh no, swing, no, that was the wrong time. Oh, there you go, look. You're swinging them forward when you go forward, you're kicking them back when you go back, and you're getting into the natural rhythm, right? And that natural rhythm causes this big increase in amplitude of the swing. So some objects like the protractor, right? The protractor here is, it's got like a weird sound, but this has got a nice note, right? It's got a nice note to it that we were already messing around with. And you already heard though, right? You already heard, that's the note, yeah? That's the note. That's the note. That's the natural frequency. Right? You already heard me silencing this tonight because it was resonating at that natural frequency that the other was providing it. Now, this is a little bit risky because I found that.
You all signed the waiver, right, before you?
I found that my pitch is not perfect anymore, and it used to be better, and it just happened naturally, and now I can never get it just right. Right, but like that was the note. No, that's beats. I can hear the beats right there. But this is not the note, right? Like this one, like, but like, it's not the note either. It's a tiny bit. I'm like a little bit off. I'm like a couple hertz off, and the noise You think you could do it? Do you want to try it? Right, just listen to that note. I'm annoyed. I'm not on pitch. I'm not on.
Aren't they both the same?
You got it? A tiny bit, yeah, a tiny bit.
Well, aren't they
And
both
go
the
down an
same
octave.
frequency?
That's what I bet. That's better. That's better. Do you hear it? Yeah. If you get that note right, if you get that note just right, it's got to be just right. Yeah. You can get that tuning fork to vibrate with sound. You don't have to hit it, right? You can hit it with sound, and the sound will cause it to vibrate. And we call that resonance, right? That's that resonant frequency that this thing will vibrate at. Go to the next one.
Oh, no, actually,
Yep.
right.
Oh,
No, you're
good. All right, so then, right, we've got this classic, right? Wine glasses also have a nice ting, ting. You ting that wine glass, you get a nice note. And if you put a straw in the wine glass, you could try this at home. You put a straw in there, the straw will lean up against the wall of the glass, and if you can get it to jiggle just a little bit, you can knock that straw around.
My name's Chase, and I live in California, and I'm gonna try to break this wine glass
You got birds there.
by only my voice.
It's jiggling, yeah? The straw.
Mom, look. Mom, I broke it! You did not.
Don't try this at
Look
home.
it! I did! I broke a glass! I broke a glass, people! Woo! So funny! Look it! I broke the glass! I broke the glass with my voice! Isn't that just crazy?
Look at that bird going crazy. That bird knows. All right. That bird knows. All right. So this is also, I've learned that this is a win-win for you, okay? A sunset sailboat ride, and the captain pulled out this huge conch shell. That this one is pathetic compared to the one that guy had, right? But this is a tube, right? This is a tube that's just windy, right? And then you can access the end of the tube by sawing off the tip of the conch shell, right? So this is a win-win because we're either going to get that resonant frequency for you tonight, or we're going to demonstrate how I'm not vibrating my lips at the right frequency, right? Because you got to get the right frequency. That's the key to resonance. You could hear it there for a second, yeah? Yeah.
Do you have any brass players in the
I know, now that I've touched my lips to it. But this one I'm a lot more competent at, right? So we've got the shell playing competition, but then we've also got the Australian Aborigines didgeridoo, right? The more authentic would be like a hollowed out piece of wood, but this is just a big long PVC pipe. But the length of the tube, right, determines the natural frequency, and a longer tube is going to be a lower note. All right, now, this one we're going to get. I'll stay here for 10 minutes, but I'm a little bit better at this one. But I'm nervous, see? See how that works?
Yeah.
You know, I've gotten this almost right away every time, but not here tonight.
Yeah.
Because I gotta relax. Come on, we gotta get it. right? You got to slow down that vibration, right? And get into that nice frequency, the frequency that the tube determines, right? Not me. All those other efforts are just like, nope, that's not it, nope, that's not it. This is the one, right? There it is. All right, almost here at the end tonight. I had another little demo for you. Let's see this guy. Let's get this guy to work, right? All sorts of things that we can get going, right? And make to vibrate at their natural frequencies. Yeah, that's like the middle right there. This is some rosin. And again, this is like, your hands are sweating, Mr. Klimas. Right? Got to get all these things to work. Right? And the rosin, right? The rosin gets you to like stick slide, stick slide, stick slide, stick slide, right? So that you can make that note, right?
You can even make it with your hand.
Vibrating, vibrating, not vibrating, yeah? The node, the antinodes. But like, what if we went like right in here? Is that about the middle? What do you think?
Yeah.
Like right in there, yeah? Like pinch it right there. So now we're doing quarters, right? We're doing quarters. Instead of that second harmonic, we've got the fourth harmonic. And then if we're really lucky, we could do like the eighth. The eighth is hard to get. Ooh, I heard it talking about. I'm inching my fingers down.
There it is.
Yeah, there it is, right there. Right, there it is, yeah? And all those stringed instruments too, right? They're just like a little bit more familiar, yeah? And this guy is a little bit. All right, so we got the singing rod, and then we got this guy right here, a little bit fancier. We've got, right, if you can't see, just feel free to move around here. We've got our, three different length pieces of metal on there, and they're jiggling, right? So now we're starting at 30 hertz. What we're going to do is we're going to increase that frequency. And you can see that these guys just died down, especially if you're getting up in here. Oh, right there now, right in there. You got this guy jiggling a ton. You got these two guys that are almost standing still. We've got that resonant frequency of this longer piece. Now I'm at a lower frequency here, like 68 hertz. And you can see that the end is really jiggling an antinode. Because these guys are cinched together, you got a node there in the middle. And so now we're going to go up from there. And that's going to die down. But at a higher frequency, right, we're going to start to get into that resonant frequency of that shorter piece, right, the medium length. And we're getting that guy an antinode on the end with a node in the middle, about 100 hertz right there. And if we keep going, right, that oscillation dies down. And I'm looking now at the shortest of them. Ooh, like right in there, right? We got that jiggling going here on this piece. These two guys have really stopped. I mean, they're vibrating, right? But they're not getting that dramatic increase in the amplitude, right? We're not at that special frequency that's gonna do the job for those. And so instead of that piece, right, we could take a look at this one, just something a little different.
Ooh. It's gonna be fun.
And jiggle this hoop. Ooh! Do you see that huge oscillation right there? No, you don't. You got to see like this, yeah? Is that better? Right? You got a really nice oscillation right there going. And if I keep, let's keep going, all right? Kind of died down. But if we go and we find the next nice one where nothing really is happening here, it's jiggling, right? But it's just not right. Where are you? Where are you? I think I might have missed. Oh, no, keep going, oh, there we go. Right there we have it. Let's find it. Right now, I'm just fidgeting around a little bit. I'm looking for that oscillation to be the biggest. Ooh, it just died down there. Let's find it. Oh, there it is. Right in there. And you really got, right, node, 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 because it's cinched together there. Node and antinode, 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 antinode. That'd be like 1, 2, 3, 4, 5, like the fifth harmonic of that loop, right? A special frequency, a frequency that really gets it going. All right, and then to finish off things tonight, this one, I don't have the fancy equipment, right? I've got here this plate, right? It's a nice backdrop, but that's not what it was meant for. It was meant for to be put in here and then to jiggle the plate, right? And have this plate jiggle. And now you've got like a two-dimensional platform and you sprinkle sand on here, all right? And I found that this is not particularly impressive because what I need here is a sine wave generator that'll go ridiculous frequencies. And so instead what we've got for you is a final video, all right, to finish things off, a final example of resonance, all right, on a plate, and we're good?
Yep.
And you sprinkle some sand on the plate. You sprinkle some white sand so that you can see it. Now, if the sand is at a node, it'll stay put because the jiggling is minimal. But if the sand is at an antinode, it gets jiggled off, right? It gets flung off. And over time, the sand will fall off the edges, all right? But then you sprinkle some more on, all right? And then you just keep going through frequencies here, and you see how those frequencies will, right, make the plate vibrate. I can get the first of these going, all right? But this one, I can go up to 400 hertz on that little device that I've got here today. But this thing starts already past 345. We're almost at the limit of what I can do, right? The sand jiggles off the antinodes, and it accumulates at the nodes, right? But where are these things? Well, now they're like in 2D. And as those frequencies go up, the patterns get more and more complex and more complicated. Because as the frequency goes up, the wavelength goes down, right? And that in 2 dimensions here, though, you got this, you can still even see, right? You can see how it's getting pushed, right? It's getting pushed by the jiggling of the plate in some parts. And already now we're 32, 40 hertz. And if you notice too, we're skipping, right? So we go in between and we just get a lot of noise, right? We just get a lot of nothing, right? So, oh, look, we got another special frequency, a frequency that resonates. So I would say it would depend, right? It would depend on the thickness of the plate. And it would depend on, right, what the plate's made out of, right, how heavy it is. And I would say that, yeah, like I bet you would get different things with different subtle variations. That would be my guess. Yeah, I would assume that if you use that same plate, you're probably going to end up with the same patterns again when you do it. And you can note down all the frequencies, right? And so you would know kind of what to zone in on to find it. Because there's definitely a lot of trial and error and a lot of lost sand. If you what? Yeah, I don't think so. I think you would get something different. I think it would be different. Correct. They're jumping, right? This is just a nice video editing right here. Yeah. Yep. I think that, right, this is just like my most advanced application to show you tonight, right, of resonance and how that relates to the standing waves that are formed on that plate and the interference, right, of the waves that are all jiggling around and bouncing around. So, thank you. Thank you all. I hope you were entertained. I'd be glad to take lots of questions if you've got them, but hope you were, right, informed and entertained tonight.
I like the last one.
Right, the end.
All right. So, do we have any questions here in the audience? Hold on, I'm gonna.
Have you been able to generate what we saw in the video with that one?
Yeah, so only that very first pattern, right? It's like a pretty, and it's not, you know what, I haven't even like compared to like say, wait, is this the exact same pattern? I didn't even look. I was able to get kind of like a simple little one that happened, right? And that thing goes up to 400 hertz. And that very first pattern that was in the video, at least, was like 300 and something, right? 300 and whatever. So you needed higher frequencies to really make some more of it, right? And so, you know, philosophy of teaching is like go big or go home here. All right. So I wanted to go big with all the demos that I do, and this one was like, you know, like I'll just show the video. I think the video was better than what I can show you tonight. I can show you some things, right? I tried to show you as much as I could. But I also relied on other things too, other videos that can do it better than I can.
What's your question?
Can I eat the gumdrops?
Can you eat the gumdrops? I think they're.
Well, you know, I mean, I wouldn't recommend it, but
We don't know where they've been or how long they've been there.
I think that if your mom and dad say, okay, that these ones, right, you know, right, you can eat these gumdrops. They're still in the package.
Let's see. We did have a question out on the live stream from Only in Antarctica, which is actually really in Toronto. Do massive constructive ocean waves exist where two waves in equal height collide to form a massive dip in the ocean?
Yeah, so I would say that this is something that it's at the limits of what I understand, right? So the simple answer is that probably, yeah, right, probably. And that the simple thing about waves is that the depth of the ocean determines the speed of the wave. I know that this is a complete oversimplification, right? But it's a nice place to start. And it's partially true because when you go down to the beach, the waves that are coming in from the deeper water into the shore, they start to slow down and drag on the bottom because it starts to get real shallow and eventually nothing, right? And they fall over themselves. That's the breaking of the waves that you get at the ocean. That the top of the wave maintains its, right, it has inertia, and so it keeps on going, but the bottom of the wave kind of starts to drag on the shallow bottom, and so it slows down, and the whole wave crashes and falls over itself. So on the simple understanding, all the waves out in the deep water all be going at the same pace, so they're not going to overtake each other and, you know, collide and stuff. They're just going to, you know, kind of travel along nicely. But I know that that's not true, right? I know it's not true because I would enjoy body surfing down at the Jersey Shore when I'm a kid, and you go out there, right, past the, you know, kind of like where those waves are breaking, and you wait. And as a physics teacher now, I know that you wait until you kind of get those two that come together, and you got a great ride in because you got a real nice one that kind of was like, whoa, and it happens quick, right? And if it happens kind of right where you are, you can catch it and ride it in. So, you know, my answer is like, yeah, probably, right? Probably.
All right. We have another question from the live stream. Joe asks, some of the sand patterns were not symmetrical, and why is that? Is that perhaps imperfections in the plate?
Yeah, exactly. So there is, what is it, CY sigmatics, something like that, which is like this whole study of that Chladni, Chladni. That's what we saw there at the end, the Chladni plate. I don't know how to pronounce anything, I just read it.
Okay.
The Chladni plate, and that cymatics, CY, like matics, I'm pretty close if I'm off by a little bit. It's like a whole branch of almost like music and stuff. There's a great video that you could find. It's like Niels, somebody who does all these different kind of weird things, right? Like making those non-Newtonian fluids, like oobleck,
yeah,
and putting it on speakers and having it like right, go into all these crazy patterns. And so my guess would be like, yeah, probably, right? But this is like its whole, you could like really get deep into this, and I would assume probably that there's got to be imperfections, right? This is a truth that I know as a teacher, right? Everything that I teach as a teacher is an oversimplification, right? And the reality is always way more complicated. And so like you think that plate is an even thickness, you're wrong. Right? It's definitely not. And like this would be like the perfect experiment to say like, ooh, we could use this experiment to like almost verify different imperfections in the plate. Yeah.
All right. Any other questions here? Oh, hold on. Let me take the mic over here.
So a lot of these are like sound, and we can see with the slinky stuff. What about like light? Do they have those waves that add up or cancel each other out?
Yes. So light is its own presentation, right? I can come back sometime and we could do a whole thing on light, right? Light is the one and only, right, non-mechanical wave. A mechanical wave meaning mechanical waves are waves that require a medium through which to propagate. So the water waves need water, right? This needs the whole thing here, right? But like slinky waves need the slinky. But light is its own very unique thing that has been, right, very bothersome in the history of science and of physics, right? That the light travels through the nothingness. And therefore, what the heck is it? And what is it jiggling? And it's jiggling the ether. Oh, there is no ether. And so, like, it's an electromagnetic wave. Well, what the hell does that mean, right? Like, it's an oscillation of an electric field and then a magnetic field. Well, how do I know those things are real? Like, well, you can detect them, right? And then, but they, like, self-propagate each other through even the nothingness of the vacuum. So, right, light gets into its whole other way because we don't see the wave, right, of light. Like, you could see this wave. Oh, transverse right here, right? You can see that, right? But light we perceive in brightness and in color. And does light interfere? Absolutely. It's called the double slit experiment, where there's this pattern of light and dark dashes on the wall because the light has come through these two openings and it's diffracted and it's interfered with itself and it's created light and dark and light and dark and light and dark and light and dark. See, light is clearly a wave. But then light gets into all this other wonky weirdness and you're like, oh, I don't really know anymore what the heck it is. And so I think it's like its own show. It would be, right? The light show instead of the more visual mechanical wave show that I did tonight.
Thank you.
I actually have another question. You didn't touch on it, but I'm wondering if you maybe could comment a little bit about Doppler.
Yes. So Doppler I didn't do tonight at all, right? But Doppler is, right, when something approaches you, it is chasing its own waves and it's compressing them. And so what you hear is a higher sound that's being emitted, and as something leaves, right, you get the waves being spread out because you're running away from your own waves, and the sound is then perceived as lower, right? What's actually emitted is just one note, but you hear something higher and lower. And so I didn't do any Dopplers today because I was focused more on this like interference and standing wave and resonance, and Doppler doesn't really fit into any of those. Doppler's like its own phenomenon, I think.
Right.
It would be like a fourth one to add to the mix, right? I kind of did a little introductory stuff tonight, but then I was, you know, interference and standing waves and resonance. Doppler would be like its own little thing, right? And you can move by the ambulance once the ambulance is stopped on the side and you get Doppler, but the ambulance can also come by you when you pull off to the side, right? So you can have a moving source and you can also have a moving observer. And then, of course, light does this too, yeah?
And everything in between. Actually, we do a program in the summer. We're doing one again this summer where we have our students talk to an astronaut on the space station using radio. And radio, in fact, will do Doppler. In fact, so when we are tuning our radio as the International Space Station is flying toward us, we actually have to transmit lower in frequency because it's coming at us, and he can't change his frequency, so I got to transmit lower so that he's hearing me higher as he's coming at me, and then as he goes past the point of close approach, I then have to transmit a little bit higher in order for him to hear me correctly. So and we do the same thing in astronomy. We talk about redshift and blueshift on you know, when looking at stars, and like the James Webb is going to be looking at everything in infrared because we're going to be looking at the beginning of the universe, and basically everything that's so far away, that's just moving far away from us, we won't even see it invisible because that visible light has Doppler shifted into the infrared.
Right. Very interesting.
Well, thank you. Let me see if we've got any other questions here from the web, or any other questions here? We have a question. Yeah, you have one. What's your question?
I forgot.
Okay.
Yeah, I play with the spinner. So what kind of wave does the spinner have?
The like the fidget spinner?
Yeah.
Yeah, so I would say I messed around with those a little bit, and this doesn't really fit, right? Like we get these phenomena that are like related, but they're not quite the same, right? So it's not like that fidget spinner isn't propagating through a medium, right? I mean, we're looking at it, that's light. You know, you can maybe hear it, but that's sound. But like the spinner itself isn't really like right? It's like A wave. Now, I have a strobe light in my classroom, and I put the strobe light on the fidget spinner, and that is amazing, all right? Because you can get these, it's spinning forward, but because of the way that you're sampling it with your strobe light, you can get it to move back and then move this way and that way and all over the place. But to me, that's like I don't know, I'm not seeing, at least right here, I'm like, is that really like a wave? I'm not, to me it's a repetitive thing, right? So there's repetitions involved, there's cycles involved, like waves have cycles, but I don't know, to me it's like different. It's like it's a different thing.
It's sort of like a motion picture. Like you look at like a car commercial, and sometimes it looks like the wheels are moving backwards. When you look at the spokes on the wheels, it's because you're only getting a small little snippet of information, and then you're seeing where is that snippet of information a little bit later.
You get to open your eyes here, and then you get to open your eyes here, right? And then you get to open your eyes here, and then you get to open your eyes here,
Right.
and then you get to open your eyes here, right? And you yeah. But to me, that's like that like gets into like a sampling problem, right? That's a great engineering thing, right? Sampling and right, over and under sampling and all that business.
All right, well, I wish we had some stars to show you tonight, or something to show you tonight, but tonight this clouds are not going to do it. But I really want to thank you very much for I just love this stuff. I mean, this is so thank you very much, and I especially appreciate your enthusiasm. And I wish I was about N number of years younger and could be going to your class at school here. So anyway, so well, we're going to finish up with a live stream. But if you have any other questions, why don't you go ahead and ask Peter. So thanks again. Really appreciate it.
You're welcome. Thank you all.